This is the 13th session of part 1 of this lecture series. And today we will focus on a quick detour to discuss Hilbert transform and its application in signal processing. We will not go into mathematical details and talk about harmonic analysis, but we want to see how Hilbert transform can help us and when it can help us. So there are several references. The left-hand side is a very standard digital signal processing textbook used in electrical engineering. The right-hand side is a standard textbook in harmonic analysis. In case you have interest, you can consult them. What is Hilbert transform? The definition is very simple. It is 1 over pi, and this is PV, means principal value, and there is an integration. And I will not go into details about principal value. What you can imagine is this is actually a convolution. You can read it as a convolution of the function f and the 1 over t as a kernel. Although this 1 over t looks very weird, right? It's very bad. It's not at a 1. It blows up at 0, blah, blah, blah. But anyways, you can define it using principal value. And its outcome is very interesting. If you have a cosine function, then the output is a sine function. Okay, that's a very, very basic principle that we use in signal processing. Or sometimes it says that the angle is rotated by 90 degrees, okay, in a complex domain if you do it. Okay, so an immediate consequence of this process is a suggestion that we can get instantaneous frequency using Hilbert transform. Why? Because if I give a function f which is cosine, then we can define a new function f theta, which is cosine plus I Hilbert transform cosine, which becomes exponential I to pi t. And if you remember, we mentioned that this one is called real form function, and this is called complex form function. And the real form can be recovered from a complex form by taking the real part. But how to recover a complex form from real form? In this very specific case, we can use Hilbert transform. But what about in general case? That is the topic we will go into today. So once we get the complex form, then we can get the amplitude modulation by taking the magnitude and get the instantaneous frequency of the derivative of the phase. So that is very good, isn't it? We get instantaneous frequency, we get amplitude modulation. But in general, sorry, it doesn't hold in this way. It doesn't hold in this way. And there is a usual terminology you may see in practice. It's called analytic representation of a function. That is this guy. You just have general function. If you can define Hilbert transform, then you sum them. The very specific property of Fa, this analytic representation, is that it will only preserve the positive frequency content of the function f. So it looks good. But as I told you, it has some limitations. And I will start with some limitations and then tell you when we can use it, or when and how we use it. The first example is this very, very simple, again, cosine function. It contains 2 components. The first one has frequency 1. The second one has frequency pi. So there are 2 components. This is not a multiple of the fundamental component. There are 2 components, and this is the function. Now you can run Hilbert transform, very nice, because Hilbert transform itself is a linear operator, so you will get exponential I plus exponential I to pi pi t. So you can get amplitude modulation, as we discussed, which, well, looks very weird, isn't it? Oscillatory, but positive. And instantaneous frequency, which is the derivative of the phase, is, well, what is this guy? It's very kind of not easy to interpret. In particular, you get negative frequency. What is it? What do we get? Right? This is something maybe not easy to interpret. And that is somehow related to the notion of instantaneous frequency. What do we mean by frequency? And the Hilbert transform in this case may not be used. And the simple solution to it is, we know there are multiple components, 2 components. Then we should do some decomposition first. And after decomposition, we can study each one. And this is another view of this similar situation. But this time, let's focus on the wave shape function. Let's say, okay, now we have one component, but the component will oscillate non-sinusoidally with two components. First, you have 2 pi t, and this is 4 pi t. So this is frequency, the double of the first one. And now I just make everything analytic. Everything's perfect. There's nothing we need to worry about. Hilbert transform, blah, blah, blah. This is the real part of the original signal. And this is another signal. The only difference is this is 0.99, this is 1.01. So if you pay attention to these two signals, they look almost equivalent. The only difference is cross 0 here, if there's a small cross, and there is no cross here. So, if you pay attention to these two components, and you evaluate their Hilbert transform and get a phase, what you see is, hey, this guy, the phase is not monotonic, but the phase seems to follow the gray line, and the gray line is the phase of this 2 pi t, the fundamental component. Okay, so it's good. But for this component, for this function, when the higher frequency component is slightly higher, then it becomes monotonic, but it deviates from the fundamental component's phase. So what's the problem? What's the problem? The main problem is actually the winding number, because of the winding. So you have two components. So in a complex domain, you have actually one oscillation and two oscillation. And this guy, it doesn't really pass 0, but this guy, it passes 0. So you get one extra winding. That is why you will get some kind of phase jump because of the winding. But here, there's no cross, so it has some weird phase behavior. And the consequence is the frequency of instantaneous frequency of this signal will have negative ingredient. But what does it mean by negative frequency? And that is directly related to the phase. What does it mean by phase? That we will discuss in the next session, or the session next. So it tells you that, well, Hilbert transform is good, but it has some limitations. And another limitation is the sensitivity to trend. For example, I give you cosine 2 pi t, but now I add a very, very slow, low frequency component, which is just like a smile curve. And this is the Hilbert transform. As you can see, there is a discrepancy. And this is the estimated amplitude, which does not make too much sense, isn't it? Because the main component is this guy. The amplitude ideally should be constant 1, but it has some weird fluctuation behavior. And the instantaneous frequency, again, doesn't make too much sense, right? It's just, well, what is it? Again, the solution to this issue is we should do some pre-processing. For example, if we know there is a trend, very low frequency component, and to avoid some properties of Hilbert transform in the frequency domain, which has some jump near the frequency 0, low frequency region, we may better to decompose the signal first before we apply Hilbert transform. That will be one solution to this issue. And let's take a look at a real respiratory signal. This is a respiratory signal, as I showed you. And based on what I have shown you, it is obviously a non-sinusoidal oscillation. Then this is the Hilbert transform, which looks maybe okay. That will be the amplitude modulation, which is very weird. The blue one is the estimated amplitude modulation. You cannot say it is wrong, right? But it is also weird. And this is the instantaneous frequency, which is jumping too fast, too much. And it is difficult to say what do we really get. It's difficult to interpret physiologically. This is a respiratory signal, so we have physiological knowledge. So at least to me, it's difficult for me to do too much interpretation. Okay, so now, finally, let's take a look at an example where Hilbert transform is commonly applied and when it is useful. It can be very useful. So in this example, you see f of t is a cosine function. Okay, and this cosine function has some time varying frequency. Okay, and it has amplitude modulation. Okay, it's an amplitude modulation. And the red one is the Hilbert transform of function f. And now we can get an estimated amplitude modulation, which is very nicely, coincident with the true amplitude modulation. And we can also get the instantaneous frequency estimation. The true is the red one. The blue is the estimated one. There are some boundary effects which you can ignore. And you can see, hey, it works very well, isn't it? Unlike the previous examples, we can get amplitude modulation function and instantaneous frequency. And why so? Why so? There's a very interesting observation which will lead to the main theory I will discuss today. So this is a signal, and now if you focus what? You focus on exponential 2 pi, but this is 0.5 cosine t, this part. Okay, only this part, and forget about 40. Forget about 40. Just focus on this part, and you consider its complex form. And you have the amplitude modulation in the beginning as well. So that will be the function called capital F. And in this capital F, its power spectrum is shown below. And what you see is something very interesting. Its power spectrum is supported near 0, which is not super surprising, because this guy has frequency roughly around 0, and this guy is a very, very low frequency component. So the multiplication in the frequency domain convolution is also low frequency. But I have drawn a red line here, which is -5. Technically, I should draw in -4, but let's see, -5. You see, there is totally no energy on the left-hand side of -4. This is -4, sorry, -4. Okay, this is -4, this is -4, should be -4. Okay, whatever. So, you see, this is a very interesting observation. Will there be anything in general? And the answer is yes, and that is, to my knowledge, the foundation of a communication system. But I'm not really in communication system, whatever. It is the Bedrosian and the Nuttall theorem in 1963 or 1966. So the theorem states in the following way. It says that if I give you two functions fg in LP, okay, and now let's have some assumptions about the Fourier transform, and in particular the support. If the Fourier transform of f is 0 for every frequency per c less than -a for some a positive, and the g of Fourier transform is 0 for any frequency content less than a. A is non-negative, so -a is on the left-hand side, a is on the right-hand side. So what you can see is g, okay, is g has high frequency content, and the f has low and probably high frequency content. Okay, and in this, if this is the situation, if this is satisfied, then the Hilbert transform of f times g will be f times Hilbert transform of g. And this very looks very simple formula turns out to have a dramatic sequence. And that is the plot of how this is related. An immediate application is this something called narrow band signal model. Narrow band signal model. So as you may remember, this is something we have seen quite often. This A is amplitude modulation, but this time we will have something slightly different. We have C0T, this is high frequency sinusoidal carrier, okay, and you have some frequency modulation called phi. So this is the scene that is slightly different from what we discussed, because before we have 2 pi phi of t, but now this time this is the C0t, which is a sinusoidal carrier or carrier frequency, and you have some modulation. So that is the model, which is called narrow band signal model. And this is called narrow band signal model. We can understand it in the following way. Suppose we take function f to be a of t, and exponential I, which is the complex form of cosine phi of t. You forget about 2 pi to C0. This is f. And then you take g to be exponential e 2 pi cos C0t, which is the high frequency component. So now if you do some calculation, you will see that the support of g hat will be one point called cos C0, right? Because in the frequency domain, this is a delta major at cos C0. And now we only need the Fourier transform of f to be 0 for any cos C less than minus cos C0. Okay, suppose this hold. Then by Bedrosian or Nuttall theorem, you know Hilbert transform of fg will be f times hg, which gives you the desired formula. And hence, you can get whatever you like, that is, the cosine becomes sine, so that you can reconstruct the complex form of this narrow band signal. And then you can recover amplitude modulation, then you can recover the frequency modulation because C0. Why is it useful? Because usually the C0 is a high frequency carrier frequency. It can be very high. So that you have a lot of bandwidth that you can host the information that can be encoded in AM part or FM part. So to my knowledge, that is how, if you do the radio, you listen to the radio, that is how they encode signal or voice or everything in amplitude or phase. Okay, so if f cos C0 is high, then you can include a lot of information inside A and the phi, so that if its power spectrum is 0 or one side single side banded, okay, then you can get something you like, and which is good. And the proof is actually quite immediate. You just do some calculation. For example, you take the properties of Hilbert transform of the cosine function, and you just plug in everything, change integration order. But surely, every step you need to carefully check when and why you can do it. Okay, but this is a very simple overall idea. I will not go into the proof step by step, but you can check it and see in the end. Suppose the basic assumption hold, that is the frequency content assumption hold, then you have sine of cos C plus eta will be sine A plus sine eta, and so that you can get the exchange of the order. And there are several papers that you can check if you have interest. And you can even quantify the error, and the quantification of the error is similar. Suppose FQ is what we really want, that is really the sine part of the cosine, and this FH is what you can do using Hilbert transform. Then you can just do some calculation using L2 norm to evaluate their difference, and go to the frequency domain and just plug in everything and use the relationship in between F and G's spectral content. Then you can manipulate and finally get the error quantification, which actually is the non-single side-banded content energy less than minus C0. Okay, so that also tells you that if FQ is equivalent to Hilbert transform, if this holds. So that is the quantification of the error. And let's take a look at another example. So this is a signal which I wrote here, which is not easy to read, but this is the real part of the signal. This is instantaneous frequency. This is the Fourier transform, okay, of Fourier transform of the signal. Then what you can see is in this signal, actually, the frequency content is greater than -15. Okay, so everything is good. You can recover everything. But in the next example, sorry, the instantaneous frequency changes too fast, so that there is too much leakage. There's too much leakage to the left-hand side of the spectral content we need. So in the end, the instantaneous frequency or the recovery is slightly deviated. Okay, and there are two small topics that I want to just mention. So Wagner in 1972 claimed that the Hilbert transform is the only operator that does not violate certain fundamental conditions of demodulation. This, okay, amplitude continuity and differentiability, okay, phase independence of scaling and homogeneity, harmonic correspondence, that is cosine will go to sine and so on. So there will be some kind of conditions, and they claim that, oh, if all these conditions are satisfied, then this is Hilbert transform. But Wagner didn't really finish or provided a full proof, and a proof was provided recently under the assumptions. For example, if you have I operator, and this I operator is linear and continuous, and the maps exponential I to ct to this guy, then I must be a Hilbert transform, and you can check the paper published in Archer maybe back in 2013. Okay, so which tells you that Hilbert transform maybe is fundamental. It's fundamental if you want to keep those physical quantities. And if we want more, we may need to think more generally. And there's the final slide about the high carrier frequency impacts in the amplitude modulation, adaptive harmonic function in the complex form, which is actually looks very complicated. You can read it if you are interested in later, but it only tells you that actually if you have an amplitude, you have an adaptive harmonic model function, which in general, the frequency may have support in the negative frequency. In general, it's not analytic. But if it's in a complex form, what you can do is you can multiply it by some high frequency carrier, shift it to the right hand side, so that after the shift, the frequency, the spectral content in the negative frequency is very, very mild. Then you can do the truncation, estimate the phase and amplitude, and shift the phase back, because you know the carrier frequency. But in general, if you are working with the complex, the real form, then this may not be the case. Because if this is the spectral content of the complex form, then the real form, you will have some kind of you will have some mirror, and the negative frequency component will be missing, and we need some more technique to do something. I think that is it for this session. Thank you.